Okay, so here is a contour plot. So transitioning to the next topic, here's a contour plot, and it's actually, the function is rate of change of snow fallen with respect to time and elevation. So this is a multivariable rate function. It's a multivariable rate function. Probably have never seen one of those before. Okay, so it's a volume of snow fallen, and volume in some units cubed. Unit is unfamiliar, but units cubed, and then so it's volume of snow fallen per time and per 1,000 foot of elevation on a mountain. Okay, so this is a warm-up to make sure we're understanding this graph. I want you to talk through A and B here. So using the contour plot, interpret the situation using sentences or verbally describing. Elevation of 3,500 feet at 1.4 hours. So what is the situation? What does this graph tell you about the situation at 3,500 feet above sea level and 1.4 hours, say, after the storm, the blizzard began? And then similarly, 1.8 hours at an elevation of 5,000 feet. So what is this graph telling you? So we got to understand the graph first. So get a partner and talk through these two. Everyone's talking to somebody. Everyone's got a partner. Go. Okay, what do we think here? So, Andre, can you tell me? What about this? What's the situation at 3,500 feet and 1.4 hour? 1.4 hours. Just what's the situation? What does the graph tell you?
Well, I'm not totally sure if it's just like the volume of snow or the rate of change.
Okay. So which is it? So does this graph tell us volume or rate of change? Yeah, so it says, the graph shows the rate of change. So what is the rate of change? What is it? 0.4. And what are the units on that? 0.4 what? Units cubed?
Per hour.
What?
Per hour.
Per hour? The output value of, let's see. So, yeah, so it should be units cubed. I was thinking the output value of the quantity of volume. Okay, so the volume is units cubed. So what would this rate function volume unit be? Units cubed per hour? Is that it? So per hour per 1,000 feet. So that's what the units on the 0.4 is. So I meant to say the volume units are units. The volume unit is units cubed. So the rate units would be, it's units cubed per hour per 1,000 feet. It's a multivariable rate function. So there's two independent variables. Okay, what does that mean? So what does the meaning of this? I'm going to give it a shot. Apply what we've learned. Does it mean that the rate of change is 0.4 volume unit cubed per hour per 1,000 feet? What does the 0.4 mean? Jackson, Winston.
Is it like given like
You're
the same
Jackson.
change in like time and elevation, like a small change,
Okay.
then the amount that the snowfall will change by 0.4 times that change?
Okay, so given a small change in what?
Time and elevation.
Given a small change in time, and also a small change in elevation. This tells us that. 0.4 tells us that.
That's how much. That's like multiply 0.4 times that change to get how much. Get the change in snowfall.
Change of.
Volume.
Right. So now we're make a small change in time and a small change in elevation. This 0.4 tells us that the resulting change in volume of snow over that change in elevation and over that time will be 0.4 times the change in time times the change in elevation. Or in other words, changes in volume are the rate of change times the change in both independent variables. And those don't have to be the same, right? So you don't have to have the same change in time, change in elevation. Now, there's one more qualification about these changes, right? These changes have to be?
Not zero.
Well, certainly not zero, but also small, right? Small, because we have a changing rate function, right? As soon as you move away from the point in question, in this case, that point right there, as soon as you start moving away, well, the rate changes. So then, Scott, you got to keep small changes and assume you have a constant rate right there, right? Assume you have a constant rate right there and you make a small change, and then you're good. But if you're making big changes like half an hour or 500 feet, well, then your rate is different by the time you get there, and you can't, this isn't really accurate. Yeah?
So if one of your changes is zero, how would you interpret? Would you like have to just need a whole different equation?
Right, let's think about that. Because you would, keeping it the same elevation, you would get a change in.
You come with like an approximation using like the same sort of stuff we've been doing.
Would you just use it as a constant?
Yeah, so then you'd be doing up like it would be you would if that is zero, then you'd put in that value that you have, and then you'd have a single variable situation, right? So because then this would be constant, and so now it'd just be RV of t at that e times dt. Yeah. Any other questions? All right, and we can do the same thing for this other one. So the other one is what the rate of change is, what, 1.6? Given small changes in each of your independent variables, your change in volume would be 0.6 times those changes of time and elevation. Okay, so multivariable rate function. So now we want to estimate the average rate of change of snow from 1.4 to 1.8 hours and from 5,000 to 6,000 feet. And so the average rate of change is like an equivalent constant rate of change over that associated region in the plot. So we want to estimate, if we were to look at from 1.4 to 1.8 hours, so say from here to here, from there to there, and from 5,000 to 6,000 feet, that would be this part of the contour plot right here. So is there a constant rate or a changing rate? Definitely changing, right? It's changing throughout there. But if you had to pick one rate of change that represented what was happening in this time span and for this change in elevation, what would it, like if you had to kind of guess or kind of estimate and pick one, so what one rate of change kind of models that situation? So maybe agree with the person next to you. So can you come up with single rate of change for that whole combination of intervals?
This one's fairly
All right, what did you guys come up with? So again, it's just an eyeball, just an estimate. What number might you slap on there and say this one value of rate of change kind of represents the rate of change for this time change and elevation change? What do you think? It's an estimate, so there's no risk of making a fool of yourself. Right? What? 2. What do you think? 2. Does 2 represent kind of the overall average of rate of change in that? You're shaking your head. What do you think? 1.6. So this is what? 1.2. This is 1.2, 1.4, 1.6, 1.8, and 2. Did you do that on purpose? So what about 1.6? Yeah, it's something like that, right? So like if you just consider that this goes across this corner and this goes across this corner, and then we've got these other two. So if it were off from 1.6, it might be what? A little bit less than 1.6? 1.5 maybe? Let's call it 1.5. All right, so we estimate that the R sub V is approximately 1.5, and that's going to be our units cubed per hour per 1,000 feet. And so we can use that then, maybe, see it? Estimate the volume of snow that fell during this time and during this elevation range. So if we just call it 1.5 rate of change for that whole thing, now we can get a kind of a quick estimate for as time changed from 1.4 to 1.8 hours, and you went from between 5,000 and 6,000 feet, about how much snow fell. Go. So about how much snow fell in that time frame and that elevation range. Okay, Yanni, did you make some progress on this? Tell me what you think. So that's dt? Yeah, so I called this t and this e. It's not going to be negative. Yeah, 1,000, so it's just a 1. And so what does that equal? We got a number that says 0.6? And then what are the units on that? Yeah, volume units, right? So whatever the volume is. So does it make sense what we're doing? So given that rate of change, assuming that it's the same over that entire block, where you have a 0.4 interval of time, and the range on the mountain of 1,000 feet from 5,000 to 6,000 feet, this would be the amount of snow that fell. Okay, so now we answer that same question again, but this time, so any questions about that? Does this make sense? So we're going to answer that same question again, but this time, we're going to partition that region into 4 equally sized rectangles, and then estimate the total volume of snow again using separate volume calculations for each of the 4 subregions. Is the task clear? This is where I'm going to take attendance. You're going to do this while I take attendance. So rather than throwing a constant rate on the whole thing, you're going to now break it up into 4 equal rectangles, just according to the grid there. and estimate the volume that way. So do we expect a less accurate or more accurate estimate when we do this? More accurate, right? Because now we're kind of looking more finely at different rates in there, rather than slapping one rate on the whole thing. We break it up further and get 4 separate rates. Then that should be a more accurate result. So can you do that? So do the same thing, estimate the volume of snow for that same period of time and same range on the mountain, elevation range, but using 4 separate calculations. Break it up. Okay, what's the strategy here? Let's see. Travis, tell me just the strategy, the overall strategy. What are you going to do?
So first I estimated the center points of each of the 4 quadrants.
Okay.
And then I multiplied each one of those individually by the change in y, which is 0.5.
Okay.
Times the change in x, which is 0.2.
Okay.
And that's how we answer that.
All right, so we've got so for each one of those separate rectangles, we have a dt of, he said?
Wait, 0.2.
0.2, and a de of 0.5. Agree with that? Okay, very good. And so then you said you did what in each rectangle?
I estimated the center point.
Okay, so let's go through these here. What did you say?
1.4.
This one here?
Yeah.
So you're saying 1.4. Okay.
1.8.
1.8. This one?
1.3.
1.3. 1.6. Is that close to what you did? So now we're going to pick a constant rate for each of the 4 subregions. And what are we going to do with that constant rate? So this 1.4, we're going to do what? Multiply this by change t and change in e. And then do that for each one of them, and what? And then add them together. Is that what you did? Good. So the general idea is that overall dv is going to be what, like dv1 plus dv2 plus dv3 plus dv4. And each one of those is going to be, so this first one will be, how we get dv1? 1.4 times 0.2 times 0.5. And this is going to be the same for all of them, right? Which is is that 0.1? So dv2, we're going, let's go across here, it's 1.8 times 0.1. dv3, is that 1.3? And then dv4, 1.6. And what do we get for that? What is it? 0.61. And what is this number telling us again? 0.61 is what? Change in volume due to time going from 1.4 to 1.8 hours, and then that whole range of the mountain, 5,000 to 6,000 feet. And what was it before? 0.6? Okay, so this is, we kind of can be a little more confident in this answer, and then our previous estimate was very close to that. So our previous estimate turned out to be maybe better than it normally would be for that large of a rectangle, or something like that. I don't know. But this is, we can be more confident in the accuracy of this, or that it's a good estimate. Okay, any questions on that? Is it feeling like calculus? Yeah, Right, it's calculus, which is multivariable. This is like now we're looking at what? Accumulation in a multivariable scenario. Given rate of change, you know how fast a quantity is changing, but with relative to two variables, how much do you have, right? So this is half of calculus. Given rate of change, given how fast something is changing, how much do you have? Well, this is now, we're applying this in the context of a multivariable function. Okay, so let's take it a step further here. So now I want you to estimate or write an expression. Can I erase what's on the board? Write an expression. Oh, I shouldn't have erased it that quick. So really then, what we just did was a double sum of rate of change with respect to t and e, right? We summed up. We could pick a t value and sum pick an e value and sum across the t's, and then pick another e value and sum across the t's. So we're really doing like a double sum, right? We're summing a bunch of rows, and in each one of those rows, we're summing a bunch of squares. So this is a double sum of t's and e's. Okay, so now let's write an expression that would represent the volume of snow, the same volume of snow, same total volume of snow, but now using a billion subregions. Or maybe a trillion. If I split this up into a trillion subregions, what expression could I write that would be the volume of snow for, say, a trillion subregions? What's that? He wants double integral, right? So as things get really small, we know these sums of a gazillion parts so super small intervals. Is gazillion a real number?
Yeah.
Is it really? Oh. He said, yeah. So if we use now a gazillion super small intervals, this thing becomes, double sum becomes double interval of the rate function. So we're introducing double integrals, but when you look at a double integral, you're thinking about what you just did. You're thinking of it as what? You're breaking it up into subregions and you're summing up lots of little bits of volumes of snow, each one considered kind of at a constant rate, right? So if you make that interval small enough, you can consider having a constant rate in that little region, and then you can multiply the change in volume, and then you add them all together. And then we're adding a bunch of rows together, and each row is a sum, right? Oh, but so what was it? So the t was from what to what? 1.4 to 1.8. So we're going to use limits of integration here, 1.4 to 1.8. And the e was from 5 to 6. So this now is, if you use a million or a billion, it's like, at some point, it's close enough, right? So it's small enough that we just call it a day, and we say this is the exact volume. Exact. Okay, so now I want to isolate. I'm going to look just at this Blue. So really when it comes to the integral, it's really the integral of an integral, right? So if we took this rate function with respect to t from 1.4 to 1.8, that would be its own integral. And then we're going to have the integral of that. So what I want to talk about is then what exactly does this represent? What are its units and what kind of thing is it? Is it volume? Is it rate of change? And is it time? Is it elevation? Something else? So what is that I put the gray parentheses around here? Just identifying that interior integral. What do you think? Yeah.
Is that like just the change of volume with respect to time?
Okay.
So, or
Yeah, John.
The volume of snow that's fallen for a change in time.
Okay, so he's saying it's a volume. Is this a volume? Is this a volume of snow for that change in time? Yes or no? So rather than focusing on in terms of time, what we need to focus on this thing is in terms of elevation. Because really, what I'm asking you is, look at it this way. I'm asking you what that is. So rather than focusing on time, the real way to answer this is to focus on elevation. What is that? If it's the integral from 5 to 6, something dE, what is that something then? Tell the person next to you, right? So let's talk about this. So what is that? So first of all, you're saying it's an elevation. She's saying it's a rate of change. Is it a rate of change or an amount of accumulation of quantity? It's rate of change, right? With respect to E, it's rate of change. Rate of change of what? Yeah, so this is the rate of change of volume with respect to elevation. Right? So if we were to accumulate our multivariable rate function with respect to time from 1.4 to 1.8, it gives us a single variable rate function, right? With respect to elevation. It's kind of what's left to do, right? So that's not a quantity of snow. That's not a volume of snow. It's volume per elevation change because it's still a rate of change, but it's now a single variable rate of change. Does that make sense? Okay. So let's go back to the four, the partition of 4, and let's look at. I'm going to show you the Okay, so here is the surface that is this rate of change function. Okay, so this surface is the R3 version, the surface version of this rate function. So I want to go back to looking at the 4 squares. So how would so we isolated these 4 squares, right? Here. How does that show up in this R3 rendering of that graph? So first of all, this region right here. How is that represented? How could we represent it in this graph over here, the surface? Where or what would that be? Yeah, right.
Wouldn't it be the volume underneath the curve?
Okay, so you're a little bit ahead of me. Okay, but so I'm just asking about this much of it right here. Yeah. So yeah, it's good. But what is that right there?
It'll just be like a square of surface area on the curve, right?
On the surface?
Yeah.
So this right here wouldn't be on the surface. Yeah, so in this case, the time elevation plane. So this is like time here, right? And elevation here. So we'd come out here to what, from 1.4 to 1.8, is that right? Do a good drawing here, 1.8. And then elevation from 5 to 6. So that's back there. Okay, so far so good here. Except for this right here. Let's make this a little better. Okay. And then what? We partitioned it. Like that, right? And our 1.4 to 1.8 is on the x-axis, and then the 5 to 6 on the y-axis. And so then what did we do? We took, these are our little DEs over here, right? And these are our DTs. And so when we did this, dV equals, we did what? Rate times dt times dE plus rate, etc. So how is in this drawing, how is the rate represented? So that we looked at this first rectangle and we picked a rate to be a constant rate for that little rectangle there. And how do we see the rate geometrically or visually on this graph? So how do we see the rate? I think we picked, for this first one here, this would be what, lower right corner. So this is, we got to make sure we got our orientation right. This right there would be the lower right corner, but this corner right here. And what did we say the rate was here? 1.6. So the numerical value 1.6, how does it show up on this graph for this square right here? 1.6. Surface is an object, 1.6 is a value, right? So 1.6 would be the z-coordinate, right? The z-coordinate. So it would be the z-coordinate. So if you take dE times dt times the z-coordinate, geometrically, what kind of thing do you get? So I'm going to take dE times dt and then times a height, which is the height determined by, something like this surface here. So what is that? Yeah, exactly. Rectangular prism. Does that show up? Perfect. And so this little calculation that we did, a rate times dt times dE, in the R3 rendering of the rate function can be considered volume of a rectangular prism. As a geometric equivalent. That's not as meaningful as we know rate times change. Rate times change in independent gives us a little change in the dependent, in this case volume. That's more meaningful, but it's equivalent to this geometric kind of representation of the volume of a rectangular prism, or like a rectangular tower. And so then all four of these towers will have slightly different heights, and the height's determined by the rate function, right? So this, we say this tower is 1.6 high, and then this tower is whatever, however we estimate it. But then rather than have the rates be based on estimates, like eyeballing the rate in each thing, we want a more systematic way of doing this. So we could use what's called like, use the corners, right? So if I said, let's use the lower right, lower left corners. So then rather than eyeballing for the whole rectangle, we would just pick off the rate right there at the lower left rectangle and then assign that to this rectangle. And then same with this. This would be the lower left lower left corner of this one, and we assign it to this. And then lower left, we assign it to that rectangle, and then lower left, assign it to there. And that way we'd all get the same thing, right? So for that upper left, for this one here, we would all get, what is that? This would be 1.6. And this one would be, oh no, sorry, this is 1.2. This is 1.2, and this would be 1.6, and this would be 1, and this would be like 1.4. Do you see that? So this is using lower, I'm saying use lower left corners. Now that's, you have to be careful because where are the lower left corners over here? So for the one I drew, where's the lower left corner? It's there. You see that? That's the lower left corner that we would say, I don't know, I think it's really boring too. That would be, what, is that the 1.4? What's this 1.4 here? Yeah, because this is, I got this right? This is the lower right rectangle, would be here, and we're using the lower left corner of that rectangle, which would be there. And so then, yes, this right here at this point is where the rate is, 1.4, and so then that's the height. That's the height of that rectangle, 1.4 times dt times dE. Gives me the amount of snow, but it also gives me the volume of that rectangular prism, and I could do that 4 times. But you just got to be really careful about when you use lower right, upper right, lower left, etc. That's relative to the x and y plane, and you got to get the right orientation here in R3. Again, lower left is going to be for this one right here. That's lower left. That's lower left, because looking at it this way, lower is here, left is here. So then what does the in a volume perspective, we know that this was our volume of snow. But then there's a different volume we're talking about now. The volume, what? The volume from the surface defined by that rectangular region up and down. So this is also volume between xy plane and the surface. Defined laterally by this large rectangle, right? So defined laterally by this rectangle here. By the planar region. So that planar region gives us the lateral limits of that. The bottom of it's the xy plane. The top is the surface. And so it's like what? Instead of adding rectangular prisms now, it's like sticks, right? So when you get a really fine partition, it's like you're summing up the volume of like super narrow sticks. But they're really still rectangular prisms. They're just really skinny. Okay, but so then one last question is it really truly volume? Is double integral really truly volume or something else? Pick it up there next time.